Hello and welcome to the Midnight Scientists. As the universe is unwinding around you and your curiosity is beginning to drift into dreams, tonight we are taking a calm, quiet journey to one of the most serene and yet most extreme destinations in all of space, the heart of a collapsed star. We will drift toward the quiet remnants of brilliant giants, stars that lived with immense energy, transformed in a final, powerful release, and left behind something so dense, so profound, and so quietly influential that even time and space curve gently in their presence. These are the neutron stars. Tiny, heavy, mysterious objects that exist at the very edge of our understanding and ignite a deep and peaceful wonder. So, wherever you are tonight, perhaps tucked under warm blankets, curled up on a comfortable couch, or simply floating in that soft, pre-sleep space between thoughts, allow your mind to follow the sound of my voice. Let this journey guide you into a state of deep and restful calm. This story is for educational and relaxation purposes. Now, breathe slowly. Get comfortable. The stars have transformed, but here, all is calm, all is quiet. Chapter 1: The Stellar Nursery. Long before a neutron star is born, before the collapse, before the final brilliant flash, there is a cloud, a quiet, sprawling nursery made not of brick or stone, but of elemental gas, fine dust, and the recycled essence of other long-departed stars. These are the great molecular clouds, and if you were to gaze upon them from a great distance, they would appear as delicate, glowing wisps floating in the deep, silent darkness of the interstellar medium. Inside these clouds, gravity is at work. Patiently, persistently, it begins to draw the sparse matter together. A star begins not with a sudden event, but with a slow, gentle gathering. Over immense stretches of time, countless particles in the cloud begin to cluster, drawn to each other by gravity's invisible, persistent embrace. Imagine the softest of whispers calling matter home. More mass brings more gravity, which in turn gathers even more mass. It is a quiet, feedback loop of creation that culminates in a soft, ethereal glow. Eventually, a protostar forms, a knot of matter that grows dense enough and warm enough to ignite the gentle fire of nuclear fusion. This is the moment that turns a cloud of dust into a nascent star. In its core, hydrogen atoms, the most basic building blocks of the universe, begin to merge under immense pressure, forming helium and releasing a steady flow of energy. This energy pushes outward a gentle radiation pressure that perfectly counters gravity's inward pull. The result is a state of beautiful, delicate equilibrium, a main sequence star, suspended between collapse and expansion, glowing serenely in the vastness of space for millions or even billions of years. But not all stars are created equal. Some are small and quiet, like red dwarfs that simmer peacefully for trillions of years. Others, like our own sun, live moderate lives. And then there are the giants. These massive stars, the future parents of neutron stars, live bright, burn hot, and have comparatively short lives. To be destined to form a neutron star, a star must begin its life with at least 8 times the mass of our Sun, with some being dozens of times more massive. These stellar heavyweights consume their fuel with an impressive speed. They fuse hydrogen into helium. Then, as the core contracts and heats up, they begin to fuse helium into carbon. The star develops a layered onion-like structure as the process continues, fusing carbon into oxygen, oxygen into neon, neon into magnesium, magnesium into silicon, and on, creating heavier and heavier elements in its core. Each stage of fusion proceeds faster than the last. The hydrogen burning phase may last millions of years, but the final silicon burning phase might last only a single day. Eventually, this process reaches iron. And this is where the star's long, stable life approaches a profound turning point. Iron is a unique element in this cosmic chain. Fusing its atoms together does not release energy, but instead consumes it. It is the final ash of stellar fusion. So when a star's core fills with inert iron, its internal engine falls silent. With no outward pressure to counteract gravity, the star begins a final, graceful, and inevitable fall inward upon itself. Chapter 2. The Great Transformation, Supernova. For most of its existence, a massive star is a monument to balance. But when the iron core forms, that delicate harmony comes to an end in a matter of moments. When it does, something truly extraordinary occurs. The star does not simply die, it transforms in one of the most powerful events in the cosmos. Gravity, which had been patiently waiting for millions of years, finally becomes the dominant force. The balance is broken, and the star begins to fall in on itself. This is where the pace of events quickens immeasurably. In less than a second, the iron core, an object once the size of the Earth, collapses. Temperatures soar to over 100 billion degrees. The pressure becomes so fantastically intense that the very structure of atoms gives way. Electrons are fused into the hearts of protons, creating a sea of neutrons and a flood of ethereal particles called neutrinos. Imagine an object thousands of kilometers across, compressing into a sphere only about 20 kilometers wide, all in the blink of an eye. In that same instant, the outer layers of the star, no longer supported from below, cascade inward at up to a quarter of the speed of light. But this inward fall does not continue forever. It meets the newly formed incompressible core of neutrons. It is like a wave crashing against a shore of impossible strength. The falling material rebounds. This rebound, combined with an outward rushing energy from the neutrinos, creates a powerful shock wave. That shock wave travels through the collapsing star, reversing its implosion into a spectacular expansion, blasting the outer layers into space in an event known as a Type II supernova. For a brief period, a single transforming star can outshine its entire home galaxy, releasing more energy in a few seconds than our Sun will in its entire 10 billion-year lifetime. To a distant observer, this appears as the sudden birth of a brilliant new star in the sky, a guest star, as ancient astronomers called them. One such event was witnessed in the year 1054, recorded by astronomers in China and the Middle East. The remnant of that very supernova is visible today through a telescope, the beautiful expanding filaments of the Crab Nebula. The star's material is scattered across light years. The elements forged in its core, carbon, oxygen, calcium, and iron, are flung into the cosmos. These elements become the building blocks of new stars, new planets, and perhaps eventually new life. Every atom of iron in your blood, every bit of calcium in your bones was born in such a stellar transformation. It is the universe's grand method of recycling. And at the heart of this luminous expansion, something remains. The collapsed core survives the blast. This is the newborn neutron star. Chapter 3: The Anatomy of an Impossible Object. A neutron star is born. Let us pause and appreciate the sheer wonder of this object. It packs more than the mass of our entire sun into a sphere only about 20 kilometers wide, roughly the size of a city. This is a realm where matter has been compressed so tightly that the familiar rules of chemistry and physics are rewritten. Let's contemplate its density. A single sugar cube-sized piece of neutron star material would have a mass comparable to Mount Everest. Such an object, if brought to Earth, would pass effortlessly through the planet, its immense gravity pulling it directly toward the core. So what is this material exactly? Let us peel back the layers in our minds, starting from the surface. The atmosphere is a layer perhaps only a few centimeters thick, a thin veneer of superheated plasma held in a tight embrace by the star's incredible gravity. Beneath this is the outer crust. This is not a gentle shell, but a solid, crystalline lattice of atomic nuclei and a sea of free-flowing electrons, 1,000,000 times denser than anything on Earth. Deeper still is the inner crust. Here the pressure becomes so great that it overcomes the forces holding atoms together. Electrons are squeezed into protons inside the nuclei, creating more and more neutrons. This is the region of neutron drip, where neutrons begin to leak out of the atomic nuclei, forming a kind of neutron-rich fluid that coexists with the solid clusters. And then we arrive at one of the most wonderfully strange concepts in astrophysics, the postulaire. Here, between the crust and the core, the intense competition between the nuclear forces and gravity arranges matter into complex and beautiful geometric shapes. Depending on the density, the models reveal long rods, flat sheets, and interconnected blobs. Because of their resemblance to terrestrial forms, physicists have given them familiar names: nuclear spaghetti, lasagna, and gnocchi. These bizarre structures are thought to form the strongest material in the entire universe, over 10 billion times more resilient than steel. Below the posta, we reach the outer core. Here, our understanding moves into the realm of well-tested theory, as these conditions cannot be replicated on Earth. Most models agree that the outer core is a superfluid, a remarkable state of matter where neutrons pair up and flow without any friction or resistance. Imagine a liquid that, once stirred, would spin in perfect, silent vortices forever. This superfluid may also contain a small fraction of protons, which would exist in a superconducting state, allowing electric currents to flow with perfect, lossless efficiency. Finally, we arrive at the inner core. This is the heart of the mystery. Some theories suggest that at these ultimate densities, neutrons themselves can no longer remain intact. They may dissolve into their constituent parts, quarks. We will return to this strange possibility later. For now, simply hold in your mind this image: a city-sized sphere with a crust of crystalline metal, an interior of bizarre nuclear pasta, and a heart made of a frictionless, superconducting quantum fluid. It is a quiet spinning monument to the extremes of physics. Chapter 4: The Domain of Extreme Gravity. To exist near a neutron star is to experience the laws of physics in their most profound form. Gravity, time, and space itself all behave in ways that are far removed from our everyday world. The gravity on the surface of a neutron star is more than 200 billion times stronger than on Earth. The escape velocity, the speed required to break free from its gravitational pull, is about 150,000 kilometers per second, more than half the speed of light. If one were to drop a simple object, like a marble, from just 1 meter above the surface, it would accelerate to thousands of kilometers per second, impacting with an enormous release of energy. This immense gravity doesn't just hold on to matter, it also bends light. As photons of light leave the surface of a neutron star, they must climb out of this incredibly steep gravitational well. In doing so, they lose energy, and their light is shifted toward the red end of the spectrum. This is gravitational redshift. The star's light appears dimmer and redder to a distant observer than it truly is. The warping of space-time has another fascinating effect. Time itself runs differently. The stronger the gravitational field, the slower time flows. This phenomenon, known as gravitational time dilation, is a core prediction of Einstein's theory of general relativity. Near a neutron star, the effect is magnified to an extraordinary degree. If you could hover in a protected vessel just above its surface, time for you would pass about 30% more slowly than for someone far away. A few years spent in orbit could translate to the passing of many more years elsewhere in the cosmos. Space itself is also distorted. The intense gravity curves the fabric of space-time so dramatically that light from objects located behind the star can be bent around it, allowing us to see them. This is called gravitational lensing. It means a neutron star can act like a cosmic magnifying glass. It also means you can see more than half of the star's surface at once, as the light from its far side curves around to meet your eyes, creating a strange, panoramic view. These very distortions are what make neutron stars such powerful tools for scientists. By observing the way light and time behave in their vicinity, physicists can test the absolute limits of our theories of gravity. In these silent, spinning remnants, we find the keys to some of the deepest secrets of the universe. Chapter 5: The Cosmic Lighthouses, Pulsars. When neutron stars spin, they often become the most reliable timekeepers in the universe. They flash, they pulse, they send out beams of energy with a regularity that can surpass even our most accurate atomic clocks. These spinning wonders are known as pulsars. The spin of a neutron star is a direct consequence of the conservation of angular momentum. It's the same principle that causes a spinning figure skater to accelerate when they pull their arms in. As the vast core of a massive star collapses inward, its rotation speeds up dramatically. A star that once took days to complete a single rotation may now, as a neutron star, spin dozens or even hundreds of times every second. To become a pulsar, a neutron star needs this rapid spin and a powerful magnetic field. The combination creates intense electric fields that rip charged particles from the star's surface and accelerate them to nearly the speed of light along the magnetic poles. These particles emit powerful, focused beams of electromagnetic radiation, often in the radio spectrum. Crucially, the magnetic axis is usually not aligned with the star's rotation axis. This means that as the neutron star spins, its beams sweep through space like the light from a lighthouse. If one of those beams happens to sweep across Earth, our radio telescopes detect it as a regular, repeating pulse. The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell. She detected a signal that was so precise, repeating every 1.33 seconds, that the team humorously and briefly considered it might be a signal from an extraterrestrial civilization. They even labeled it LGM-1 for Little Green Men. Soon, however, other similar signals were discovered, and the true nature of these cosmic clocks was understood. It was not life, but the rhythmic breath of a dead star. Since then, we have found thousands of pulsars. Some, like the one in the Crab Nebula, spin about 30 times a second. Others, known as millisecond pulsars, spin hundreds of times per second. The fastest known pulsar rotates over 700 times every second. An object with the mass of the Sun spinning at such a rate without flying apart is a testament to the unimaginable strength of its own gravity. Many of these millisecond pulsars are thought to be recycled. They were once ordinary pulsars that slowed down over millions of years, but if they had a nearby companion star, they could begin to pull matter from it. As this matter spiraled onto the neutron star, it transferred angular momentum, spinning the pulsar up to incredible speeds. They are cosmic vampires, sipping from their neighbors to regain a fast spinning youth. Their steady, soothing rhythm is a constant reminder that even in the vastness of space, there is order, there is pattern, and there is a quiet, persistent heartbeat. Chapter 6: Magnetars, the Magnetic Titans. As if being incredibly dense and spinning at great speeds weren't enough, some neutron stars take their extreme properties even further. These are the magnetars, neutron stars with magnetic fields so powerful they defy easy comparison. In a universe filled with wonders, magnetars are in a class of their own. A typical neutron star already possesses a magnetic field trillions of times stronger than Earth's, but a magnetar's field is up to 1,000 times stronger still. We are talking about magnetic fields of around a quadrillion Gauss. That's a 1 followed by 15 zeros. To put that in perspective, Earth's magnetic field is about half a Gauss. A magnetar's field is so strong it could disrupt the atoms in your body from 1,000 kilometers away. It is so intense it can affect the fabric of the vacuum of space itself, causing empty space to bend light in strange ways, an effect that has actually been observed. How do these objects form? The leading theory suggests they are born from massive stars that were already spinning very rapidly and had strong internal magnetic fields before they collapsed. During the supernova, as the core shrinks, these magnetic field lines are compressed and amplified to monstrous levels. But this incredible magnetic power comes at a cost. The intense fields create a powerful drag, causing the magnetar to slow its rotation very quickly. Most magnetars spin only once every few seconds, sluggish by neutron star standards. The energy they lose from this magnetic braking is immense, and it heats the star's surface and powers incredible outbursts. Magnetars are known for their sudden, intense flares of X-rays and gamma rays. These events can release more energy in a fraction of a second than our sun will emit in 100,000 years. The most powerful such flare ever recorded occurred on December 27, 2004, from a magnetar 50,000 light-years away. For a tenth of a second, it was the brightest object in our sky beyond the solar system, briefly affecting Earth's upper atmosphere from halfway across the galaxy. These outbursts are thought to be caused by star quakes. The magnetar's solid crust is under incredible stress from the twisting magnetic field beneath it. Eventually, the crust can crack and shift like tectonic plates on Earth. This sudden rearrangement releases a colossal amount of stored magnetic energy, resulting in a flare. Imagine the surface of a star, stronger than any material we know, suddenly snapping, sending ripples not just across its surface, but through space-time itself. Yet for all their power, magnetars live relatively short lives. After about 10,000 years, their magnetic fields begin to decay, their flares subside, and they fade into the background, becoming more like ordinary neutron stars. Their time in the spotlight is brief, but unforgettable. Chapter 7. Glitches, Quakes, and a Stuttering Heartbeat. From our distant vantage point, pulsars appear to be the universe's most perfect clocks, but they are not flawless. Every so often, a pulsar that has been spinning with astonishing regularity will suddenly, and without warning, speed up by a tiny fraction. These events are called glitches. They are momentary stutters in the star's otherwise perfect rhythm, and they give us a rare glimpse into the complex and hidden machinery of a neutron star's interior. A glitch is a very small change, usually increasing the star's rotation rate by just a few parts in a million. But because our timing of pulsars is so precise, these jumps are easily detected. They are fascinating because, according to physics, an isolated spinning object should only ever slow down over time as it radiates away energy. A sudden speed-up means something has happened inside. There are two leading ideas to explain glitches. The first involves the star's crust. As a neutron star spins down, its shape should become slightly more spherical. However, its solid crust is incredibly rigid and may resist this change. Stress builds up in the crust until it reaches a breaking point. A starquake occurs. The crust suddenly cracks and settles into a new, more compact shape. Just like a spinning skater pulling in their arms, this slight inward shift of mass causes the star to spin faster. A glitch. After the glitch, the vortices gradually repin and the star begins a slow relaxation back towards its previous state. Observing these glitches, how large they are, how often they occur, how the star recovers, gives astronomers a unique way to probe the hidden interior of a neutron star. It's like listening to the creaks and groans of an old house to understand how it was built. Even more mysterious are the rare anti-glitches, where a star suddenly slows down. These events are not well understood, but they are another reminder that these dense, quiet objects are full of dynamic, complex, and beautiful physics. Chapter 8: Mergers, Kilonovae, and the Origin of Gold. Neutron stars often live solitary lives, but sometimes they are born in pairs, locked in the gravitational dance. When two neutron stars orbit each other, they are destined for one of the most spectacular events in the cosmos, a merger. As the two stars circle each other, they constantly stir the fabric of space-time, sending out gentle, continuous ripples known as gravitational waves. These waves carry away orbital energy. This loss of energy is infinitesimal, but over millions and millions of years, it causes their orbit to decay. The two stars spiral closer and closer together. In their final moments, they are whirling around each other hundreds of times per second, screaming silently through the cosmos. And then they collide. The merger of two neutron stars unleashes a cascade of phenomena. It produces a powerful burst of gravitational waves, a short, intense flash of gamma rays, and a unique, glowing explosion known as a kilonova. A kilonova is so named because it can be about 1,000 times brighter than the standard nova, but its true significance lies in what it creates. The conditions in a neutron-star merger are unlike almost anywhere else in the universe. Incredibly hot, incredibly dense, and flooded with an abundance of free neutrons. This is the perfect environment for a process called rapid neutron capture, or the R process. In the moments after the collision, atomic nuclei ejected from the stars absorb neutrons faster than they can decay, rapidly building up to become the heaviest elements in the periodic table. For decades, the origin of elements like gold, platinum, and uranium was a mystery. We now know they are forged in these kilonovae. On August 17, 2017, humanity witnessed this process for the first time. The LIGO and Virgo gravitational wave observatories detected the signal of two neutron stars spiraling together. Just seconds later, gamma-ray telescopes detected a flash from the same patch of sky. Telescopes all over the world turned to look, and they saw the fading reddish glow of a kilonova. By studying the light, astronomers confirmed the presence of freshly synthesized gold and platinum. This event marked the birth of multi-messenger astronomy, observing the universe with different kinds of signals at once, like using both sight and hearing. The gold in a wedding ring, the platinum in a medical device, it is very likely that these precious atoms were created billions of years ago in the brief, spectacular collision of two dead stars, a cosmic alchemy that seeds the universe with treasure. Chapter 9: The Final Mystery, the Exotic Core. We have journeyed from the surface of a neutron star to its deep interior, but we now arrive at the ultimate question, the final mystery. What lies at its very center? Here, at densities several times that of an atomic nucleus, our physics is pushed to its absolute limit, and our theories become wonderfully strange. The standard model suggests a core of superfluid neutrons. But many physicists believe that under such immense pressure, neutrons themselves may cease to exist as we know them. They might break down into their fundamental components, quarks. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up and 2 down quarks. In normal matter, quarks are always confined within these larger particles. But in the core of a neutron star, they might be liberated, forming a sea of deconfined quarks, a state of matter sometimes called quark-gluon plasma. This substance may have only existed once before, in the first microseconds after the Big Bang. The core of a neutron star could be a tiny, preserved remnant of the primordial universe. Some theories go even further. Under such pressure, some of the up and down quarks might transform into a heavier, more exotic type of quark, known as a strange quark. This would create a substance called strange quark matter. There's a fascinating, though highly speculative hypothesis that strange quark matter might be the most stable form of matter in the universe. If this were true, a neutron star with a strange quark core could be called a quark star. To detect such an object is a profound challenge. From a distance, a quark star would look very much like a neutron star. However, it might have subtle differences in its mass, its radius, or how quickly it cools. The way it deforms and vibrates during a merger could also leave a unique signature in its gravitational wave signal. Future, more sensitive observations may one day allow us to find these telltale signs. There are other possibilities as well. The core could contain other exotic particles called hyperons, or strange quantum states called condensates. It is the frontier of known physics. Each new measurement of a neutron star's properties, each new detection of a merger, provides another clue, narrowing down the possibilities and bringing us closer to understanding the true nature of matter at its ultimate density. Chapter 10. Conclusion and Return to the Stars. We began our journey in a quiet, sprawling cloud of dust and have traveled to the most extreme environments in the cosmos. We have seen that what happens after a star explodes is not an ending, but a transformation. A neutron star is not just a remnant of destruction, it is a seed for new beginnings. These objects are cosmic clocks, their pulses guiding our understanding of time and space. They are cosmic forges, their collisions creating the heavy elements that make the universe rich and complex. And they are cosmic messengers, their gravitational whispers telling us stories of their dramatic lives and profound transformations. And they have also taken root in the human imagination. In 1977, when the Voyager spacecraft were launched carrying the golden records, time capsules of our world for any civilization that might find them, we included a map. This map uses the precise timing of 14 pulsars to triangulate the location of our solar system. We use these dead stars as our return address, a testament to their reliability and our trust in the steady, predictable laws of the cosmos. A neutron star is a riddle written in mass and magnetism, a paradox of nature. It is a dead star that pulses with energy. It is smaller than a city but heavier than the sun. It is a place where time slows down, space bends, and matter takes on forms we can barely imagine. And as you drift off tonight, whether you're listening on your couch, curled up in bed, or looking up at the night sky, carry with you the quiet reminder that the universe is vast, full of endings, full of beginnings, and always, always asking the next beautiful question. Let the steady, peaceful rhythm of a distant pulsar be the metronome for your slumber. A gentle beat, a soft pulse, a flicker in the deep, dark quiet of space. It has been spinning for millions of years, and it will continue for millions more. All is calm, all is well. Sleep now, sleep well.